So my name is Peeters. I'm from the University of Western Ontario, and I will be representing the ERS team, ID 1288, which deals about radiative feedback from massive stars traced by multiband imaging and spectroscopic mosaics. This is led by a PI team consisting of Olivier Bernet and Emily Habar from France and myself. So our program basically is focused on the emission coming from photodissociation regions. And so a large fraction of the emission that JWST will observe will originate from photodissociation regions, or PDRs. And so in this figure here, you can see a cartoon of what the PDR resembles. So we're talking here about the PDR in the middle part of the figure. And so it's a region where the physics and chemistry is dominated by photons between 6 and 13.6 eV. So typically, or originally, a PDR was associated with H2 regions or massive stars. So you have your massive stars here on the left side of the figure, which will create a surrounding H2 region. And at some distance from the central stars, the ionized gas will convert into the neutral gas. And so you pass the ionization front. That's where your PDR starts. And then if you go further away from your stars, you will go until the neutral hydrogen converts into molecular hydrogen, which is the dissociation front. And then you will still go deeper a little bit. Your carbon will convert to a CO. And then even further away from the star, you basically go into the cold molecular cloud, where you find also, for example, water ice and CO ice. So we're dealing mostly, or our focus is on the PDR region, so from the ionization front up to basically temperatures around 100 Kelvin. And so the emission that you can expect from PDR is very rich. And here you see some template spectra. So on each horizontal panel shows you the emission spectrum that you can see for a particular part of the PDR. Well, first of all, it's the H2 region, so the ionized gas. Then we have a spectrum, the second panel, for the ionization front. Then we have a spectrum where you go from the past the dissociation front, and finally a spectrum from the molecular zone. And you can see it's a very rich spectrum. We have dust continuum emission. We also have some scattered light. And we have a large amount of emission lines coming from neutral hydrogen, iron, argon, neon, etc. We also have a lot of lines from molecular hydrogen once you are in the PDR. And in the red are shown emission from polycyclic aromatic hydrocarbons. So we have a very rich spectrum with a variety of contributors. And so as you can already see from this template spectra here, a lot of the emission is basically dominated by the features which are highlighted here in red, and they come from pH molecules. For those who are unfamiliar with these molecules, I have a chemical structure here. So we have a carbon skeleton in the form of hexagons, and on the edges you have hydrogen atoms. Now when we talk about pHs, you're not talking about a single molecule as shown over here, but you're talking about a family of molecules, a population of molecules. And their emission is shown here in red. This is an isospectrum of the Orion bar, and you can see that it's dominated by basically the emission of these molecules, where you have a few main features as well as a lot of weaker bands. And so just to make sure, while PDRs and as well as pHs were not the main driver or one of the 4 drivers to build JWST, I would like to point out that the mirror of JWST has exactly the same structure as a pH molecule. And so we like to say that JWST is made for pH research. Now, the key objective from our program is really understanding the physical and chemical processes in PDRs, as well as understanding pHs. So pHs, we would like to understand their chemical evolution. So these pHs, these molecules are not static. We already know from Spitzer and ISO and some ground-based observations that that these populations vary with distance from the star, so with, depending on the physical conditions. And that in turn, because pHs are, for example, the main heating source in PDRs, will influence your PDR characteristics. And so we're really interested in understanding the details of these, the physical processes as well as the chemical processes in PDRs. And so the goals of our program are first to provide the first spatially resolved high spectral resolution observation of a PDR. And we will use NIRCam, NIRSpec, and MIRI, as I will talk about in a few slides. We would like to give the community template data and science-enabling products for PDRs, and in that sense also guide Cycle 2 proposals on star-forming regions in our galaxy and beyond. So how can JWST contribute, or what's unique on JWST for this type of research? This is very well illustrated by the following slide. So if you look at this figure in the top left panel, you see a nice star-forming galaxy. And so if you zoom in this red box over here, you basically see in the top right panel an example of a typical star-forming region. So you have a massive star cluster creating an H2 region, and then at some distance from your cluster, you basically form the PDR, which is this also seen as a transition between the ionized gas and the cold molecular gas. And so if you zoom in this structure over here, this square, you will go to the panel in the bottom in the bottom figure. And what you can see now is that we really see the details of the transition from the ionizing gas to the crossing the ionization front, crossing the dissociation front, where you go from neutral hydrogen to molecular hydrogen into the molecular zone. And so as an example, here this large circle gives you the Spitzer ERS beam, so for the spectrograph on Spitzer, which was 5 arcseconds bright. And so with Spitzer, we could not single out an individual region, and we get on a single pixel all of these different regions together. However, with the JWST beam, here is an example of 0.2 arcseconds, you can see that we can clearly probe each of these key zones in the PDR individually. And so that means, as here is a little inset, you can see how the gas temperature as well as the abundances of different elements change if you go from the ionized gas to the molecular gas or the molecular zone. And so we can now, with JWST, can provide or can distinguish or resolve the individual zones within this transition region. And so we can really probe the physical conditions on a much finer scale than what was before. And that scale that JWST provides is basically the same as the scale at which, for example, chemical processes occur where you, for example, that changes the population of the pH molecules. And so in that sense, that's where JWST will contribute. As you can see from these pictures, so PDRs are not only associated with young massive stars, but you can see them basically everywhere in our universe, where you go from star-forming galaxies, ultraluminous infrared galaxies, the surfaces of protoplanetary disks, etc. So it's a really large fraction of the emission that JWST will see represents emission that is coming from these PDRs. In addition to this high spatial scale, JWST provides also the spectral scale. And if you look here at the middle panel of this figure, and I lost my mouse. So if you look at the middle panel, you can see in black the ISO-SWS spectrum of one of the main path features at the resolution of 1600. And as a comparison, you see the Spitzer ERS spectrum at the resolution of varying between 60 and 130. And you can see with Spitzer, you basically see 3 components in this spectrum. Well, if you look at the ISO spectrum, you see multiple subcomponents and substructure, and this is exactly the substructure that let us know something about how, in this case, the power population changes chemically with distance from the ionizing star. And so in combination with the high spatial resolution, the high spectral resolution, we also have a high sensitivity, and so that means that weaker bands are also more easily detected. And so this, together with the long wavelength coverage, basically gives you the superb advantage of JWST if you are interested in PDRs. And so our team consists out of a core team of 20 people. So it's led by 3 PIs. And then we have 17 co-investigators, whose names are given over here. And then we had an open team philosophy. So anybody who was interested could sign up. And so we have now in total 125 science collaborators. And so we're covering 18 countries. And the team demographics are shown here in this pie chart. So we have a 40 to 60% female to male ratio. We have a large fraction from European countries. And the second largest fraction comes from basically US. And then we have a contribution or collaborators from a whole variety of countries, going from Asia, South America, Japan, and Canada. The expertise on our team is very diverse. We have approximately half of our team members are primarily observers, so astronomers. Then we have about 25% or a quarter that are physicists or chemists who do experiments in the lab. And then we have a quarter who are her primary focus is theoretical modeling. And so this expertise from both experimentalists as well as theoreticians is needed in order to do a full interpretation from the data that we will get with JWST. And so our target is the Orion bar. So this is the prototypical PDR. It's been observed a lot of times before with other instruments. And the reason for that is because it's nearby. It's at the distance of 414 parsec, and it's an edge-on PDR. And so that means we can really trace the structure as that simple cartoon that I showed at the beginning of the slides, going from the ionized gas, crossing the ionization front, crossing the dissociation front into the molecular zone. So that's the big advantage of the Orion bar. It also completes 2 sources which will be observed in a GTO time, which are the Horset and NGC 7023. And we have a total time of about 30 hours. So on the image you see in the background the HST image of from the Orion bar region. And superimposed on that in the red color scheme is a recent picture from ALMA. And you can clearly see that here is another reason why JWST will bring this field forward by a large leap. And that is that instead of a nice, well-defined structure where you cross particular zones in the PDR, you can see that the structure is very irregular. We have some filaments, we have globals. And so that means that now with such a high spatial resolution, you can actually probe the dynamic processes that are going on as well in PDRs. And so that's an important part of the science goals that we are also looking at. In our field of view, I want to point out that we also have a probelet, which is shown in the top right panel. So that will also be covered by our program. And so if you now look at the white box, that's the field of view of our next image. And so this is the background on which I will show you our observations. So we have here in blue the ionized gas, S2H by H alpha. Then we have the In green, the pH emission, tracing the neutral gas, and so between the blue and the green, you're probing the ionization front. And then in red, you see a molecular gas, where you can also probe the dissociation front. So labeled here are also the key zones in the PDR. And so the observations that we propose to do are as follows. We have a near-spec IFU Mosaics at the highest spectral resolution available. And we're going to cover a wavelength range from 1 to 5.3 micrometer. And so the mosaic is oriented such that we cross the edge structure of the PDR, going from the ionized gas, crossing the ionization front into the PDR, crossing the dissociation front, and into the molecular cloud. We will also do the same type, roughly the same field of view with the MIDI IFU. So this has a spectral resolution between 1500 and 3200. And there we do the full wavelength range between 5 and 28 microns. In addition to these IFU mosaics between 1 and 28 microns, we will also do imaging. Given that Orion is very, very bright, we have to do a smaller readout for the MIDI, the smallest readout for the MIDI instrument. And so in white, you see roughly the box that we will achieve with mosaicing with MIDI. And we will do that in the pH filters, 7.7 and 11.3, as well as in the dust continuum filters at 15 and 25.5. And at the same time, we will do NIRCam parallel observations. And I believe that will be in the bracket alpha line, the molecular hydrogen line, a pH filter, and dust continuum filter. And then we also have NIRCam observations. So the NIRCam field of view is very big. So these 4 square boxes that you see, rectangular boxes, are the NIRCam field of view. And so they cover a much larger area than what we will do with the IFUs and the MIDI imaging. And we will do a range of filters, probing the ionized gas with Paschen alpha and bracket alpha. We also have filters on the molecular gas, so H2, in a variety of lines. We also have the pH filters, and I forgot to mention the iron filter for iron 2. And so we also will have some continuum filters as well to look at the dust continuum. Design enabling products that we will provide have three flavors. The first flavor is enhanced data products. So we will provide maps of integrated lines and bands from the IFU spectroscopy cubes. And we will also provide template spectra from the ionized gas, the ionization front, the dissociation front, and the molecular zone. So they can be used by the community if you do not have that spatial scale that you can resolve them. The second type of products are products facilitating data reduction and manipulation. So in case there will be problems with the stitching of the spectral orders in the IFU wavelength range from 1 to 28 microns, and we will provide some insight in that problem, and if it can be generalized, we'll provide a tool to stitch the orders together. We will cross-correlate our spectra with our images and provide some tools in that sense. We will give, we basically are modifying PAFIT, which was developed by J.D. Smith and collaborators for the Spitzer, and we are converting it to Python. It's open source, and we will extend it so it works on JWST spectra, both in extended wavelength range as well as enhanced spectral resolution. And then we'll also give a list of all the lines and bands that are present in our data. And then finally, we will provide some data interpretation tools. We will provide an online tool for H2 fitting, which will, once you give in your molecular hydrogen fluxes for your maps, you get back excitation temperature, column density for molecular hydrogen, and the ortho to para ratio. We will provide a PDR model toolbox where you can basically put in your data that you have for your object and get back, for example, the strength of the radiation field, the density, temperature, etc. We will provide the pH database spectral analysis tool. This is a tool that already exists and was very successful with Spectra, and so that will be extended or enhanced to work on JWST data. And then we'll also provide an ionized gas line toolbox in the sense that we will provide diagnostic diagrams for key species to convert the line intensity into physical conditions. And so I want to wrap up with saying that JWST will see a lot of emission from PDRs from our local Milky Way up to galaxies at redshifts 3, 6, etc. A large fraction of the emission from PDRs will originate from polycyclic aromatic hydrocarbons, and so the key objective for JWST, and in particular for this proposal, is understanding the physical chemical processes in PDRs and understanding the chemical evolution of the pH family. And I thank you for your attention.
Thank you, Els, for that informative talk. Does anyone on the line have questions? Well, I have a question. So this is an amazing program. I have to say, when I first heard about it, I said, Orion, it's going to saturate everything. And so I understand you'll be doing short exposures, but are you have any concerns about bright saturation making it difficult to experiment?
Yes, so we run the numbers and we talk to people from the instrument teams. Mm-hmm. And so what we did is we modeled the emission spectrum of the Orion bar at the spectral resolution that we will observe in the different zone. Now, this is based on the knowledge that we have right now. And then we compare it with what we could do with, on the ETC to check whether we will saturate. And so we may saturate in the neon 2 line, as well perhaps in the dust continuum at longer wavelengths. Mm-hmm. And so in that sense, what we did is our mosaic is not done in one go. So we first do the weaker areas, and then we only do the ionized gas at the end because the neon 2 line and the dust continuum will be strongest there, so that it doesn't influence the observations from the weaker part. Because we had to split it up, that means that some of the tools provided by Space Telescope will not work to combine all our spectral cubes together. And so we have to make our own tool in that sense. And we also went to the smallest subarray for mirror imaging just because of the dust continuum. Now we have talked to especially MIRI, the longer wavelengths is an issue, so we've talked to the MIRI instrument team, and so they have basically advised us to do this strategy. And they have confirmed to us that even if you would saturate, for example, in a few pixels in the neon 2 line, it will not wipe out the rest of the observations or the observations after that, because that's basically the last part that we will be doing in our AOR. And so by the time JWST moves to the next target, those latency effects should already be gone. But we have looked into it. We may saturate, and that will complicate our observations for sure.
Okay. And then I had one science question. So, people talk about James Webb finding lots of stuff because it can go faint. But I think the spectroscopic thing with the spectral resolution and sensitivity will have an equal number of discoveries. So just be in the spectral domain. What are your anticipations on what you might discover by looking at this region that, like you said, people have studied a lot, but you're looking at it with a new capability?
Yeah, I think one of the problems with Spitzer was it was very faint. It was very sensitive, but it had a very low spectral resolution if you use the ERS. And so that means some of the features were just no detection or 3 sigma detection. And then I'm talking like it's not in a sense. My background is pHs, so I'm thinking about pHs. It's not in a sense about discovering new features, but it's about detecting the features so they're strong enough so you can actually study them. And also combined with the spectral resolution, seeing if there is any substructure in those weaker features, which so far has not been done. And so I think I agree with you that the combination of the spectral resolution, that the spectral resolution in these stories is equally important. Yeah.
Okay. Well, very good.